This video will be demonstrating the use of the Java-based Matrix Calculator to solve a system of linear equations by using Gauss-Jordan elimination on an augmented matrix. The system's equations that we're going to solve is given above. As you can see, we have 4x plus 5y plus z equals 6, x plus 9y minus 7z equals 10, and negative 8x plus 10y minus 6z is equal to minus 9. We form the augmented matrix that we will use Gauss-Jordan on by forming a square matrix which is filled with the coefficients of the x, y, and z on the left-hand side of the equation. We augment that square matrix with an additional column into which we place the constants from the right-hand side of the equation. Thus, the augmented matrix is that given below. I have filled in the augmented matrix into columns 1, 2, 3, and 4 on this calculator. Column 1 are the coefficients of x, column 2 are the coefficients of y, column 3 are the coefficients of z, and column 4 are the constants. Down and below are input areas that we can use in order to instruct the calculator to perform the row operations or other operations on this matrix. For recovery's sake, I would recommend that before you start and every time you complete a calculation, you take and you store the matrix as it exists in the spreadsheet, so that should the next step produce an error, you can always come back and correct it. That can be done by selecting over here to the lower right the phrase that says save as, and it gives you a choice of matrices to solve it in. I'd recommend that you save the original in matrix A, and when you say go, it has taken and stored that 3x4 matrix into A. And should something happen that we change it for some reason that we didn't want to, we can always go back, say display A, and it returns it to the original form. Gauss-Jordan elimination says what our objective is to reduce the coefficient matrix to the identity matrix with a 1 in the upper left-hand corner and 0, 0 in the remaining columns. In column 2, we want the second element to be a 1 with zeros in the first and the third. And in column 3, we want the third element in 3, 3 to be a 1 and zeros in the rest. We will allow the constants to float so that when we're finished, we will be able to read off the solution. You can use any of the Gauss-Jordan operations, but if you'll notice in this particular one, there's already a 1 in the second column. So what we could do is go down here and says exchange row 1 with row 2. That will move row 1 into row 2 and row 2 into 1. So if we say go, you can see it's done that interchange. I'd now recommend that you save this as matrix B so we can get back to the original in case. Okay? Say go. Once we've done that, we now want to reduce each row, a row, so that the element below the 1 in column 1 is a 0. And we do that by performing a row operation. We can do that row operation in the following fashion. In order to do that, we can apply a row operation that says take a non-zero multiple of one row, add it to another row, and replace it to that second row. In this case, we're going to take a non-zero multiple of row 1, that is negative 4, times each element in row 1, and add that to 1 times the elements in row 2 and store it in row 2. When we say go, the calculator will perform that operation. And as you can see, we have reduced row 2, column 2 to a 0. We now want to reduce row 3 by performing a row operation using row 1, but this time we want to do it on row 3. And in order to do that, we're going to take 8 times row 1 and add it to 1 times row 3, which will give me a positive 8 plus a negative 8, which will be 0, and store it in row 3. And thus I've reduced the first column to a unit column with 1 in the upper left-hand corner. I now want to pivot, and that's the term applied to the element that I want to remain fixed, and then reduce the other two. I want to pivot about row 2, column 2, or the negative 31. I want that to be the unity, or 1. So I am going to take the element in row 2, and I'm going to multiply it by a positive 1 over 31. I'm sorry, a negative 1 over 31. And that should give me a positive 1 in that location. If I say go, that indeed does. I'm now going to save that so I can go back to it. Okay, now I want to reduce the other two. In order to reduce row 1 to have a 0 located there, I want to take the elements in row 2, since that's now my pivot, and I want to take negative 9 times what's in row 2 and add to that 1 times what is row 1, and that will be a negative 9 plus 9, which will give me a 0, and I want to put that into row 1. As you see, it has done it to everyone in row 1, every element in row 1, but since the zeros were in row 2, it left the column 1 alone. I'm going to do this with, let's store that in B so I can get back to it if I want to. And now I want to reduce the third column, and I can do that by taking a negative 82 times what is in row 2 and add to it 1 times what is in row 1, and that should give me a 0 there, and I want to place it up. I don't want there, I want row 3. I almost made that mistake. I want to take what is in row 2, multiply by a negative 82, and add it 1 times what is in row 3, and store it in row 3. And when I do that, I've now reduced column 2. I'm going to store that one in row A so I can recover it in case I make a mistake. Now I want to pivot against another. This time I want to use the element in row 3, column 3. Okay? And I want that to be 1, so I'm going to multiply what is in row 3 by 31 divided by 456. And that should give me, by row 3, and put it in row 3, and that should give me a 1 there if I did it correctly. I'll say go, and sure enough it did. Let's store that one in A so we can get back to. Okay, now I want to reduce the other two to have zeros. In order to do that, I'm now going to use row 3, and I want to add 29 31sts of row 3 and add that to 1 times row 2 and put the results in row 2, and that should produce a 0 in that location. Sure enough it does. And now I want to reduce row 1. So I want to take negative 44 31sts times row 3 and add that to 1 times row 1, and that should reduce that to 0. And it does. Once I have arrived at the reduced echelon form with 1s on the diagonal, I now can read off the solution to my original equation. In that equation is solved by the ordered triplet of x equal to 223 over 114, y is equal to negative 49 over 456, and z is equal to negative 587 over 456. The solution to the original system equations X is equal to 223 over 114. Y is equal to negative 49 over 456. And Z is equal to negative 587 over 456. You will find the link for this matrix calculator as indicated. Special thanks to Jeff Morgan at the University of Houston for developing this Java-based calculator.